This is the 25th lecture. 25th lecture on FET differential amplifiers, and we shall also introduce today power amplifiers, that is large signal amplifiers. The circuit for an FET we already drew. We shall draw a part of it today to start the discussion, and this part is the initial part, Q1 and Q2. This voltage is VG1 and this voltage is VG2. The two sources are connected together, S1 and S2, and they are connected to a resistance R sigma. This current is ISS and this is minus VSS. The rest of the circuit is two RDs. I could as well draw them. R sub D, and these connect to plus VDD. I have not shown the source part. Let the two gate voltages be VG1 and VG2. Then the differential voltage applied at the input V sub D is equal to VG1 minus VG2. It is the difference voltage applied between these two terminals, and as usual with the BJT amplifiers, as we did with the BJT amplifiers, in the FET also we find this difference VG1 and VG2 as V, I beg your pardon, this will be simply VGS1 minus VGS2. Is that okay?
Yes, R sigma sigma.
Okay. Okay, all right. V sigma sigma, and if you want
R sigma sigma.
okay, R sigma.
I sigma sigma.
Because two emitters are connected together, so instead of one subscript we use two. Hardly matters, but okay, I agree. Do you see that VG1 minus VG2 is simply equal to VGS1 minus VGS2? Okay, is that point okay?
Okay, sir.
Right. Now we are in business. Our purpose now shall be to express VGS in terms of I sub D, because we want to calculate these two currents, I sub D1 and I sub D2. Obviously, one of the relations is that I sub D1 plus I sub D2 would be equal to ISS. There are no gate currents at all, and therefore this is a exact relationship.
So
No.
please tell again why VG2 is VGS1 minus VGS2.
Oh, VG1 minus VG2, because this point is common. So it is VGS1 minus VGS2. Okay? This is VGS1 plus minus,
VD is equal to.
and this is VGS2 plus minus. Okay? So it is the difference between the two. If I write KVL, VG1 would be equal to VGS1 minus VGS2 plus VG2, and therefore VG1 minus VG2 is equal to the difference between these two voltages. And we obviously see that ID1 plus ID2, the two drain currents, add up to ISS. Okay? There is no gate current, and therefore no assumption on beta or GM is necessary, as was necessary in the case of BJT differential amplifier. Now you also know the current voltage relationship of an FET. It is ID equal to IDSS 1 minus VGS divided by VP whole squared, provided VDS is greater than VGS minus VP. And we assume that this is true. VP is obviously the pinch of voltage. And you see that ID equals to IDSS if VGS equal to 0. Okay? That is, if you recall the characteristics, VGS equal to 0, the value of the current is IDSS. Okay? From this relationship, we can find out VGS as equal to VP multiplied by, yes, 1. I don't want to do these algebraic steps. Yes? 1 minus ID by IDSS. No. Which one is square root?
ID by IDS.
Okay, that's fine. And therefore, if I substitute in the relationship for VD, which is VGS1 minus VGS2, what I will get is VP, I am avoiding these algebraic steps, multiplied by square root of ID2 minus square root of ID1, okay, the whole thing divided by square root of IDSS. Is this relation okay? Is it obvious? All right. Let me repeat this. V sub D equal to VP. Let me write it in a more clear fashion. Multiplied by square root of ID2 minus square root of ID1.
This is an expression for VD. So VD.
VD. Right. This is an expression for the input differential voltage. Okay. And the other relation is ID1 plus ID2 is equal to ISS. These are the two relationships which, when simultaneously solved, will give you expressions for ID1 and ID2. Okay, this is our aim, to find out expressions for ID1 and ID2 in terms of VD, VP, and IDSS. And this algebra, again I leave it to you. The values are ID1 and 2 is equal to ISS by 2, 1 plus minus. It's not as simple as in the BJT case. It's somewhat involved. VD by VP, distinguish between D and P, then twice IDSS divided by ISS minus VD by VP squared. Why does the square come? Because we have squared this. Okay. VD by VP squared multiplied by IDSS divided by ISS squared, curly bracket closed, to the power half, and then this bracket closes. This is the expression. I urge you to clear out this algebra and obtain this. Even though it's a horrible looking expression, it turns out that if you plot ID1 and ID2 versus what is the variable VD by VP, then the plots are exactly similar to the plots for IC1 and IC2 versus VD by VT in the case of a BJT. In other words, one current increases, the other decreases. The plots are exactly similar. What you plot is VD by VP, and you plot here ID1 and ID2. It turns out that these currents are very similar. I should not have drawn the, well, okay, this is 0. This is 0 for the current and 0 for the voltage. I should have brought it here, VD by VP, okay? And the two currents flow like this, and the other one is like this. Exactly similar. One rises, the other falls. This is ID, and at VD by VP equal to 0, as you can see from this expression, it is exactly ISS by 2. Okay? So this current is ISS divided by 2. The maximum is obviously ISS. And we assume you may or you may not ISS as IDSS, then this current is exactly ISS. Okay, otherwise it will be modified by IDSS. But that is not important. What is important is that the plots are very similar. Okay, and therefore all that is said about BJT differential amplifier also applies here. In other words, if I find out VO1, no, what did we say? VOD. No, first we have to find out VO1 and 2. This would be VDD minus I sub D 1, 2 times RD. Okay, I was waiting for that. So my VOD is equal to VO1 minus VO2, which would be ID2 minus ID1 times RD. And it turns out that a plot of let me give you the expression by clearing the algebra. This becomes equal to minus ISS RD VD divided by VP, then within curly bracket twice IDSS divided by ISS minus VD by VP squared times IDSS divided by ISS whole squared, curly bracket close, to the power half. This is also a quite involved expression, and it is a quadratic expression.
So where is this bracket? Yeah, where is the bracket after 2 ending?
Oh, here. Thank you. This comes from the expression for VGS minus VGS1 minus VGS2. It comes from the same expression is repeated here. Okay, now this is not a linear expression. That is, VOD does not vary linearly with VD. Okay, with VD by VP, because of this square expression here. It is actually a cubic. However, near VD by VP equal to 0, near VD by VP equal to 0, the expression is approximately linear. Exactly the same way as in a BJT. Okay, and if you plot VOD versus VD by VP, it turns out that the situation is somewhat like this. It's very nearly linear, and this voltage, can you guess what this voltage would be? No? Pardon me? ISS times RD. And this voltage is, in the BJT case, it was IEE times RC, and the other one was minus ISS times RD. And these limits of linearity, it's approximately linear when VD by VP lies between minus 0.5 and plus 0.5. Okay? So these are the limits of linearity of an FET amplifier. And yes, any question? Okay, therefore we can find out the gain. Now, how to find the gain? A sub D would be, by definition, VOD D divided by dVd, and since this expression, since this curve is approximately linear, we evaluate at Vd equal to 0. Okay, and if you do that, let's take the expression. Our expression is formidable looking expression, VOD minus ISS RD VD divided by VP, then twice IDSS divided by ISS minus VD by VP whole squared IDSS divided by ISS whole squared. I am repeating the same expression. If I differentiate this and put VD equal to 0, if I differentiate this and put VD equal to 0, obviously I don't have to differentiate this expression. Isn't that right? You see, it is VD multiplied by an expression containing VD. So it's a product of two functions. Differential coefficient of this, which would be 1, multiplied by this at VD equal to 0. Alright, so we'll be left with only this term. No under root. It's under root, okay. That under root comes. The second term, we'll have VD here, and since we are putting VD equal to 0, we don't have to differentiate. These are tricks of the trade. And you have to look at the expression and do. And I can write this by inspection. That is A sub D, which is minus D VOD divided by D VD, would be simply equal to minus I. Pardon me?
Why should there be a minus sign
Before the differential.
before the differential?
Why not?
Oh, why is there a minus sign? Because the slope is negative.
What's the
Oh, I beg your pardon. AD is this. Okay. Right. This is minus ISS RD
There is no minus now.
divided by VP. There is a minus.
There would be a minus.
There is a minus. Okay. Where have I made a mistake? No, I have not made a mistake, except this one, which I have corrected duly. This is minus ISS RD by VP, then square root of 2 IDSS by ISS. It comes from this expression. And you see ISS occurs here, ISS also occurs here. So I can write this as minus RD by VP square root of twice IDSS times ISS. Alright. This is the expression for the differential gain. Now, what is IDSS? I'm sorry, what is ISS? This is twice ID. Isn't that right? ISS is twice ID. Both the currents are equal, and therefore these 2 and 2, they come out. So the expression becomes minus 2 RD by VP square root of IDSS times ID. Now, if you go back to the expression for current, what is current? ID equal to IDSS times 1 minus VGS by VP whole squared, and find out GM. GM is DID D VGS. You can show, we have shown this earlier. We can show that GM is simply minus 2 by VP square root of ID IDSS. Very simple. Differentiate this and differentiate this and substitute for 1 minus VGS by VP. Okay. Now, if you compare this with S sub D was twice minus RD times 2 by VP square root of ID IDSS.
Excuse me, sir.
Yes.
So where is GM evaluated? At what point?
At ID. At the Q point.
So is there any value substituted
No,
in the differential?
no value.
No.
No value. You see, if I differentiate this, I will get twice IDSS times this multiplied by minus 1 by VP. Okay, and then this quantity 1 minus VGS by VP I replace by square root of ID by IDSS. That's how I get this expression. Okay, and therefore you see that this is minus GMRD. I claimed yesterday that this would be the case. This is indeed the case. The rest of the analysis, as you must have guessed, except for this nonlinear voltage current relationship, voltage current transfer relationship, the
Yes, plus
that puts me
because GM is minus
GM is positive. Pardon me?
GM is negative, sir.
GM would be negative, yes, that is correct.
No, sir, GM will be positive.
Because
So
VP
what is the
is
significance of negative conductance?
So
Okay.
VP is negative.
VP is negative.
So,
So it will come out to be positive.
So GM becomes
no,
positive.
in the expression, this expression is correct?
Yeah.
VP negative GM positive.
So minus 2 by VP.
So VP is a negative quantity.
One at a time. What is the question?
Should be plus.
This should be plus? No, I have made a mistake about the sign previously, somewhere else. Maybe in VOD. Somewhere I have made a mistake about this sign. Anyway, you clear this out. This is correct. This minus sign is correct. Okay, minus GMRD. Now, what was the question? What is the significance?
How can the conductance be negative? GM is negative.
Oh, GM is not negative. You see, VP is negative, so GM is positive. But GM can be negative. You should not worry about GM being negative. What does that imply?
So current in other.
No, it's not the direction. Okay. You see, it is not the current and voltage across one pole, across the same terminal. It's a transfer relationship. So all that it means is the current direction is different. But here, GM is not negative, it is positive. I have made a mistake previously with regard to the sign of VOD. That's right. A VOD should have been positive. And that's how this has come out wrong. AD, this expression is correct. So on this page, whatever I have written is correct. Okay? Please do correct the previous sign. Now, I could have continued with the analysis of BJT differential amplifier, but since the results are absolutely identical, I would not repeat that. As I said, we will illustrate with the help of a couple of examples in the problem session. Now it is time to go to power amplifiers. So far we have talked only about small signal amplifiers. Small signal amplifiers basically are voltage amplifiers or current amplifiers, and we found out voltage gain, current gain, input resistance, output resistance. In the case of differential amplifier, common mode gain, differential mode gain, the CMRR and things like that, because nowhere did we ever mention the question of power. Now it is time, because amplifiers have to deliver power. A stereo, for example, the usual wattage that you get in the market, which is also very harsh to hear in a room like this, is 30 watts. There are stereos available with 200 watts or more than that, even more than that, okay, 200. Well, I don't know what people do with them, but if you want music, well, 200 watt is not the power. But anyway, since that is the market force and we are being driven by market forces, we should know how to design large signal amplifiers. Even 30 watts is a large signal, and you have to make very careful designs. Now, power amplifiers, basically we shall consider two kinds. One is for integrated circuit applications and the other is for discrete circuit application. Obviously, if you use a loudspeaker and a transformer with 200 watts, obviously IC is not the answer. IC power amplifiers deliver basically powers of the order of a milliwatt, maximum up to a watt. What is the limitation? Limitation is power dissipation. If you want to deliver large power, you also have to be prepared to dissipate large power. And ICs cannot dissipate large power unless you put a small fan inside or some other cooling device. Okay, there are cooling devices at gigahertz range, for example. You have to pass chilled water. Okay, and there are special silicon tunnels dug through it by integrated circuit technology to cool the device. But we will not go into that. We will consider powers of the order of milliwatt in IC power amplifiers, and in discrete power amplifiers, watts ranging to, let's say, maximum about 200 watt. All right. We shall consider both of these types of amplifiers. But since we had started, our previous discussion was differential amplifier, which forms a part of an operational amplifier or the input stage of almost any integrated circuit, be it a phase detector or a phase locked loop or whatever it is, differential amplifier. Let's continue with this. Let's first discuss what should be the output stage of a typical, let's say, integrated circuit, analog integrated circuit, like an op amp. Therefore, we first consider IC power amplifiers. And the emphasis on IC power amplifiers is as little power dissipation as possible, as few resistances as possible, as small resistances as possible, number of transistors, no constraint. You can use almost any number. Okay. Now, obviously, if we want, okay, in integrated circuit power amplifiers, the output load resistance would be of the order of, let's say, 100 ohms to maybe 1K. Power amplifier, maybe to drive a small motor or to drive something else, maybe to light a lamp, an indicator and things like that. Power amplifier is needed. On the other hand, if you go for large power, then the usual application is a loudspeaker, and therefore the output resistance, the load resistance, shall range from 4 ohms to about 16 ohms. Okay, 4 speakers in series or 2 8 ohm speakers in series. This is the usual range of load. Obviously, if you want power, then you shall have to drive large currents through the load. Okay, large currents, which means that the voltage swing, peak to peak swing, should be as large as possible. And if you refer to the usual load line, obviously the swing cannot exceed VCC, the power supply. All right. And if you want distortion-less power amplification with a single device, then obviously your Q point has to be somewhere in the middle of the load line, so that the swing on this side is VCC and the swing on this side is 0, but it cannot be exactly 0. It must be limited to 0.2, that is VCE set. If we go beyond that, then there will be distortion. Now, obviously, with such large powers, large voltage swings, there would be distortion. Distortion would be a fact of life, but we don't want it. Okay, we don't want distortion. Therefore, we shall limit our operation to as little distortion as possible. Whereas with a voltage amplifier, distortion is banned. We don't want any distortion. We will make careful designs so that the signal is indeed small compared to the value of the Q point. The signal would be limited to, let's say, this range. On the other hand, for a power amplifier, we go to larger ranges. Even if we do not touch cutoff and do not touch VCE set, there is distortion, because the characteristics are not absolutely parallel to each other. And there are small bends here, there are small bends here also when you go to large voltages, because it goes towards breakdown. Okay? So in large signal amplifiers, distortion will be there as compared to small signal amplifiers, and we shall have to design this circuit so as to minimize this. We can only minimize this. We cannot make it equal to 0. The in integrated circuit power amplifiers, obviously the swing can exceed VCC. There are two supplies, VCC and minus VEE, and therefore the effective supply is VCC plus VEE, and the effective swing can go to VCC plus VEE. This is a small difference, but that is not of much concern. Now we go back to the load line. If the Q point is somewhere here, and the signal is such that the Q point does not shift, the operation does not shift beyond the cutoff or beyond the saturation line, obviously current will flow in the device for the whole cycle of the input. If we take the input as sinusoidal, okay, take the input as sinusoidal, then throughout, if this input is plotted versus theta, then for theta equal to 360 degrees, that is during the swing of the input, during the total swing of the input, the output current shall flow. Okay, if the current flows in the device, there are operating points where the current will not flow for the total cycle. Okay, if the current flows for the whole cycle, then we call it a class A operation. These are historical names, class A. On the other hand, if the Q point is here at the cutoff point, that is at the quiescent condition, no current flows in the collectors of the device, then this is called a class B operation. Obviously, in class B, the conduction angle theta is 180 degrees. It is only for one cycle, okay, depending on whether there is a phase change or not. It's only one cycle of the input that the current will flow in the device. Obviously, if you want the device to make distortion less power amplification, obviously you require two devices. One will conduct during the positive half and the other will conduct during the negative half, and you shall have to combine them in some manner. You have to combine them in some manner so that the output looks like the input. Okay? If it is simply one cycle, then obviously it's a half-wave rectifier rather than an amplifier. But it is our purpose to amplify this signal and to be able to deliver large amount of power to the load. And well, class B, where the conduction angle for each device is 180 degrees, that is half of the cycle, either the positive half or the negative half, there are two devices needed, and historically this type of operation using two devices is known as a push-pull operation. One pushes, the other pulls. Okay, there is no other significance of this term. This was coined by one of our forefathers, and we have stayed with it. Okay, just like your father gave you a name, you can't, without an affidavit, you can't change it. Even that is not very desirable. It's not very ethical. That is questionable. But now suppose the Q point is now somewhere here beyond cutoff. Then obviously the conduction angle would be less than 180. That is, only during part of a half cycle the device will conduct. And obviously there will be heavy distortion. Okay? Maybe the device conducts only for this part. Then the output current swing shall be like this. This is the input, the output current swing will be like this. Output current will flow only for part of a half cycle, and obviously you shall have a heavy distortion. Now, this type of operation is called class C. Class C operation, despite the fact that it introduces heavy distortion, is also used. In fact, in large power applications, at radio frequencies, this is the important point, frequencies must be high enough. At radio frequencies, class C operation has to be resorted to. The amplitude modulated transmitters, the radio transmitters, use class C power amplification because of high efficiency. Larger the power, larger will be the power dissipation also, and therefore if the devices do not normally conduct and they conduct for as short a time as possible, the power dissipation will also be smaller. Okay? And therefore, class C operation is used at radio frequencies, and the distortion that originates from there is avoided by using, instead of the usual resistive load, a tuned circuit in the collector. A tuned circuit in the collector, and the output is taken from here. The tuned circuit has the property that it is a band pass filter. That is, it accepts, if the Q is very high, then the tuned circuit response would be something like this. So it is only a band of frequencies around the center frequency which would be amplified by this amplifier. Okay? You see, a current swing like this, when it passes through this, when it passes through the tuned circuit offers an easy pass to frequencies beyond the center frequency. And to center frequency, it offers a high resistance, which means that the voltage developed here excuse me, would be mainly of the frequency that you want. It is because tuned circuits can be used that class C amplifier can be used, not otherwise. Is the point clear?
Not much, sir.
The effective load here is very small, approximately 0, for frequencies other than the tuned frequency, other than the resonance frequency. Yes.
So is it so the load is very small for the resonance frequency?
Load is very high for the resonance frequency. For the frequency at which, that is omega naught is 1 over square root LC, what is the impedance of this? Infinity. Unfortunately, no inductance can be made without a resistance, and therefore it is 1 by R square root L by C. This is the impedance. So at this frequency, at the resonance frequency, the impedance is very high, and the gain is minus GM times effective load. The effective load is very high for that particular frequency, and any such current swing can always be decomposed into the Fourier series, of which the fundamental will be the one which we want to amplify. Okay, so with the help of a tuned circuit, class C power amplifier operation is possible with minimal amount of distortion, and this is the standard practice in any radio transmitter. In any large power amplification at radio frequencies, this is the standard practice. Class C operation is somewhat beyond the scope of this analog electronics class, but if time permits, we will have a look at it at a much later point. The usual power amplifier that is used in integrated circuit is class B because of its high efficiency. Class B. Why does the efficiency arise from? Because under quiescent conditions there is no current. I sub C is equal to 0, and therefore there is no quiescent dissipation. There is no dissipation at the Q point. The Q point is at the cutoff point approximately. And the circuit, I had already given this circuit in one of the tutorial sheets. The simple circuit for a class B power amplifier using integrated circuits is this, that you have two transistors, one PNP, one NPN and the other PNP in a complementary symmetry. Complementary symmetry, that is Q1 and Q2 are otherwise identical, all right. And the collector current of Q1 flows through Q2 normally if it is class A operation. But in class B, the load is connected here, and since it is an integrated circuit, we should not use any capacitor, so the load is connected directly to this point, to the common emitter point. The two emitters are connected together. Shall we call it emitter coupled? No, in a differential amplifier we called it emitter couple because we will see that there is no coupling. When Q1 conducts, Q2 is off. So Q1 current does not go through Q2. Okay, this is RL, and the input, the two bases are connected. The input signal is also applied directly. Well, this goes to minus VCC. The two voltages have to be identical now. We don't have a choice. The two supplies have to be identical in order that distortionless operation is possible. The input we cannot apply through a capacitor for integrated circuit, and therefore the input is applied directly here. We assume that the input is sinusoidal, then we shall see what kind of distortion arises. Now there is a deviation from the usual practice of notations. In small signal amplifiers we could work in terms of phasors.
So you said that the input cannot be applied through capacitor.
Yeah,
Why?
because I am talking of an integrated circuit power amplifier, IC.
But still the input you are providing from inside.
Input we are providing from outside. Okay, we will not use a capacitor. That will reduce the cost. And if you use an external capacitor, well, it's a large capacitor. It may be 50 times the size of the IC chip. But space is a problem. You want to send this into in a satellite. Well, you can't use a capacitor. Not only it's ugly looking, well, we don't mind it, but the space, the volume that it occupies. I can pack in much more because every milligram put into a satellite counts. The load. It's called the payload, as it is called. Okay, so we don't use a capacitor. Now, as I said, there would be a deviation from the standard practice of nomenclature. As I said, in small signal amplifiers we use the phasors. So you use capital V subscript small I, capital V subscript small o. Now, since we have to be concerned with distortion, we must follow the output signal point to point, and therefore we must bring back the time. And so we say our input is small VIT and the output is small VOT. Okay, we go back to the time domain. No longer the phasor, no longer the Laplace domain. We go back to the time domain. In the large signal case, it has to be done because otherwise we will miss the time exploration of the signal. Okay, how the signal changes with time. And we will use this notation that VIT is equal to capital V I M, the maximum value, let's say sine of omega t, and often we'll replace omega t by theta. The output signal similarly, if it is sinusoidal, okay, there's a big if, we shall call this VOM sine of not necessarily omega t, there can be a phase change, so sine of omega t plus, let's say, some phase phi. This would be our notation. Okay. Now let's look at the operation of this circuit. The two transistors, as I said, are perfectly matched. Okay. When VIT is 0, both Q1 and Q2 shall be off. When VIT is 0, both Q1 and Q2 shall be off because there is a voltage. For Q1 to conduct, this voltage must be VBE on. Okay, and for this transistor to conduct, this voltage VBE must be greater than So instead of talking about VBE, we will talk about VEB. For transistor Q2, we have to have the thing now. VEB2, which will be a positive quantity. VEB2 has to be greater than VEB2 on, which is approximately 0.5 volt. Okay. Therefore, when Vi is 0, there is no question of conduction of Q1 or Q2, both are off. When Vi increases, okay, when Vi increases and touches the value of VBE on, when Vi increases in the positive direction and gets the value VBE on, Q1 starts conducting. And when Q1 conducts, Q2 obviously must be off. So the current that comes from here, IC1, let's say, I am using this as a total current, but you know under quiescent conditions the current is 0, and therefore this is also the signal current. Alright, IC1 comes here, Q is off, so it doesn't find a path here, it has to flow through RL. Alright, is that clear? Okay. You also notice that when VIT is positive and greater than VBE on, the transistor Q1 acts as an emitter follower. Isn't that right? There is no load here. The load is at the emitter, and therefore this is an emitter follower. And therefore the voltage, let me put this, VIT greater than VBE on, VIT would be equal to VBE1 plus V0T. Is that clear? The output shall therefore be less than the input by this amount VBE1. When it goes into the active region, VBE1 will exceed 0.5, it may go right up to 0.7. In order not to confuse the main issue, we will assume that VBE1 on and active are the same, approximately 0.7. If it is not, you can take care of it, okay, to simplify the analysis. Alright, now what can be the maximum V0? What can be the maximum V0? Pardon me? Maximum V0. Don't think of, I am increasing Vi so that V0 can increase. But what can be the maximum?
VI max minus 0.7.
That again depends on Vi. Suppose Vi is unrestricted.
So VCC minus VCC.
That is correct. The maximum value can be VCC minus VCE set. Under this condition, when the maximum is reached, what is the input maximum? What is the input maximum? VCC minus VCE set plus VBE1. Agreed? Under this input, the outputs can reach this value. Agreed? Now, what is this value? This is greater than VCC or less than VCC? Greater than VCC, and VCC usually is plus minus 15. We hardly ever require a 15 volt signal at the input, and therefore Vi max is limited to a value less than VCC. In other words, the transistor Q1 should not be allowed to go into saturation. Is it point clear?
No, sir.
Okay. Theoretically, our maximum output is VCC minus VCE set. That is, the transistor Q1 has been allowed to go into saturation. But you know, in the saturation region there are distortions, and therefore we don't allow it to go there. And this is logical because this voltage shall be reached when the input reaches its maximum possible value, that is VCC minus VCE set plus VBE1, which, because VCE set is of the order of 0.2 and VBE is of the order of 0.7, is greater than VCC. The practical situation is hardly ever we shall require an input signal which exceeds the VCC. Where is the input signal derived from? For a power amplifier, where is the input signal derived from? From a preamplifier, which is a voltage amplifier. and in a voltage amplifier we don't allow the output swing to go right up to VCC, and therefore it does not arise in practice. Even if it arises in practice, we shall limit it. Why shall we limit it? Because it will cause distortion. Okay. Now if this point is clear, then one should be able to guess what the characteristics would be if I plot V0 versus Vi when Vi is positive. You see, Vi does not conduct till a value of 0.7. Q1 does not conduct till Vi reaches a value of 0.7. When Vi exceeds 0.7, what is the relationship? The relationship is this: Vi is equal to V0 plus VBE1. VBE1 is a constant, therefore the slope of V0 versus Vi curve shall be unity. Okay. Therefore it rises like this. Now how long can it rise? The maximum obviously shall be reached here. This is VCC minus VCE set. Okay. And at what value is this reached? This is reached at VCC minus VCE set plus 0.7. I am taking the numerical value. Okay. Is the point clear? The transfer characteristic.
So won't we take 0.8?
Why don't we take? Oh, you take 0.8. I don't mind. I have taken 0.7 and a typical numerical value. Typical numerical. I could have taken 0.5 also. But the phenomenon is independent of what you take. The phenomenon that occurs, which you will see now. Now, I go back to this circuit. If VIT now becomes negative, okay, if VIT decreases to a negative value, then obviously Q1 cannot be on, Q1 shall be off, and when VEB2 exceeds VEB2 on, exceeds, because we have taken it to be a positive value, all right. When this exceeds 0.7, then Q2 conducts, and Q2 conducts like this. The current now flows from here via this to the negative VCC, and this is why this is to be identical to plus VCC, because Q2 conduction and Q1 conduction must be absolutely symmetrical. Any asymmetry will cause a distortion. Okay, so it conducts like this, and you see V0T will also be negative now, because the current is flowing like this. Okay, and the relationships are exactly similar. That is, the slope shall again be 1. In other words, the characteristic, if I draw it on the other side, it would be minus 0.7, and then it will go like this and saturate at, can you tell me what this value would be? Minus VCC plus VCE plus
Sir, minus VEC.
VEC set. Thank you. VEC set, that will be a positive value. Then minus 0.7.
Not minus point.
Why minus? Only on the
So no minus points on it.
There will be on the input.
So that will be
Oh, that is on the input. Agree. So it can reach only. Then the input under this condition would be minus VCC, then
Plus VEC.
plus VEC set
minus 1.
minus 0.7. Okay.
Sir,
Yeah.
so is this characteristic independent of beta of the transistor?
Is this characteristic independent of beta of the transistor? Yes, it is independent of beta of the transistor, because in an emitter follower we have written the emitter follower relationship. So between V0 and Vi, we have not considered it is independent of RPi, it is independent of GM, it is independent of everything.
So
We have
that
only
means we
considered.
use different transistors like.
Pardon me? If we use different transistors, then you are in a mess. We will not use different transistors. Okay. Now, what I want to point out to you is the following, that there is a region in the transfer characteristic which is a dead band, there is no response. If V sub I lies between minus 0.7 and plus 0.7, there is no response. It is only after that, that the output voltage follows the input voltage. This is called a dead band. Dead band is approximately of width 1.4 volt. 1.4 volt. Now, what it means is that if the input voltage lies between minus 0.7 and plus 0.7, no current flows either in Q1 or in Q2, which means that if my input voltage is like this, then I draw a 0.7 line and a minus 0.7 line. The output current shall flow only from here to here and from here to here. Oh, no. Okay. At this crossover region, when the input voltage crosses from positive to negative, no current flows. So the current waveform, if I draw it independently,
So what
it
are
will.
the variables for the axis, x and y axis?
Oh, this is VI or current versus time.
So, sir, this is similar to class C operation.
Quite so. This is similar to class C operation. There is a band, that is, the input current waveform will now look like this. The current waveform by Q1 and by Q2. The current due to Q1, current due to Q2. The load current, the current that flows in the load will look like this, the waveform. Obviously, this waveform is a very distorted form, very distorted as compared to the input waveform. And this distortion occurs when the input voltage crosses over from a positive value to a negative value. So this distortion is known as a crossover distortion. Okay, and one of the obvious ways to get over crossover distortion is to change the Q point. If we maintain Q1, VBE1 at 0.7 and VEB2 also at 0.7, then this distortion shall not occur. It is also true that the crossover distortion, how do you think it will depend on the amplitude of VI? If VI increases, will the crossover distortion increase or decrease? It will decrease. We shall show it next time.